Here we go. Whoops. Wrong page. Okay.
No, you are not. I'm 5'8".
I'm always going to say my actual height.
You already
I'm
have.
always going to say 5'9".
This is not your actual.
In what year?
Taller than me.
I'm gonna go back.
Yeah.
5'11".
Well, then space wants me to store it.
Space.
The laws of time and physics broke just so glorious. Back then, 5 is fun. You're the only guy that I've ever seen that's trans height.
Okay. So we've got test number 1 on October 15th is where I've put it. But then I don't know how I missed it, but that's the Tuesday after the long weekend, Thanksgiving. So that's kind of rude. Do you guys want to have it on the 15th or should we move it to the 17th?
7.
We can move it to the 17th. Is everyone kind of okay with that?
Yeah.
Okay.
Wait. Actually, do we?
No.
We have one in camp for the 21st.
It's still the same.
Yeah, 17 sounds good.
So then it'll be on the Thursday instead.
Like communication person.
You can study as if it's on the Tuesday and then have 2 more days to study. How about that?
Yes.
So it's on the Tuesday,
Oh.
and then we have to do the whole presentation, do the slideshow.
So let's do that. So I'll kind of rejig some stuff and just because I don't want to have a test first thing 8 a.m. right after the long weekend. Because maybe it takes time to get back or whatever you're doing. I don't know. Okay. Tiny bit of review because we're going to talk more about lines today. So back to lines.
Test is on chapter 1 and 2, correct?
I'll add that here. Chapter 1 and 2. So it'll still be on chapter 1 and 2. We'll have to start chapter 3 then on the Tuesday, but it won't be on the test. So you can kind of tune it out, I guess. Yeah, just come to class, but don't listen. No, it's okay. It's not gonna muck you up. All right, so 2 lines are parallel. All right, we talked about it last day. If M1 is equal to M2, right? If the slopes are the same, then of course they're parallel, right? They're allowed to have different intercepts, but if the slopes are the same, then they are parallel. And 2 lines are perpendicular if M1 times M2 is equal to -1. Or another way that we could do it, depending on the information that we have, right? So this is what I would do. This is the math I would do if I had 2 slopes, right? If I have slope 1 and slope 2, and I want to show that they're perpendicular, then I would multiply them and show that it equals -1. Usually what we'll see in the example, not the next one, but the next one, is we'll have one slope and we want to find the slope perpendicular to it. So in that case, or M2 is -1 divided by M1, right? Just dividing the M1 to the other side, solving for M2, right? They're the same. You only need this one property, right? But usually we end up using this version of the property, right? Okay. Okay. that kind of the end of our review. Right? We talked about x-intercepts, we talked about y-intercepts for a while, right? But then we talked about horizontal intercepts, where does it cross the x-axis, right? That's where y is equal to 0, but I'll leave that with Tuesday, I guess. What if we have to find a line parallel to y equals 3x plus 1 that passes through some point? Yeah. So I'm not going to draw it myself. Let's use Desmos to draw it out just to get an idea. 3x plus 1 looks like this, right? And it had to pass through what point? 0, -2. So this line has to pass through, well, I don't think I can I? It's not letting me draw a point, but anyways, here. So we want to force a line, right, to be parallel with this line that goes through 0, -2, right? And so it's going to look like this. So now we know roughly what it's going to look like, right? We had a line, what was the y-intercept of that line? At 1, like this. And then here at 0, -2, we want to find a line that's parallel. Okay, so we have y equals 3x plus 1, which means that m1, or the first slope, is 3. If they're parallel, then m1 is equal to m2. So we already have the slope of the second line. Okay. So therefore, m2 is also 3 to be parallel. Has to pass through 0, -2, right? And so now we have y is equal to 3x plus b. If I know if x is 0, y has to be -2. Right. At 0, -2. Then I can force y to be -2, same method that we used before. If I have a point on the line, I can plug those xy coordinates in and I can solve for the y-intercept. Obviously, in this case, -2 is the y-intercept, but we're going to go through the motions anyways. 3 times 0 tends to be 0, which means that b is -2. Therefore, the line parallel to y equals 3x plus 1 passing through 0, -2 is y equals 3x minus 2. Nice. Okay. Any questions about that one? It's just constructing lines. More lines, so many lines. What if we have to do the same thing, but for perpendicular line? Perpendicular means that m1 times m2 is equal to -1. We know what 3x plus 1 looks like. Oh, sorry. I guess we can check our work. How about I put this 3x minus 2 in Desmos just to make sure that it looks good. 3x minus, oops, not times 2, minus 2. Looks good to me. Phew. The perpendicular one's a little bit, a smidge harder, I think. We still have this line, but now we want to find a line that's perpendicular, still passing through that point to 0, -2, but in order to be perpendicular, it looks like this, right? I'm gonna say this is 90 degrees, whoops. Even though it might not look exactly like it. So if they're perpendicular, then I have y is equal to 3x plus 1, which means that m1 is still 3. And I know that m1 times m2 has to be -1, which means that 3 times m2 has to be -1. Or if you prefer to just go to m2 is -1 divided by m1, that's totally fine, but they're the same. Right? So now my slope of the perpendicular line has to be -1/3. Okay. Y is -1/3x plus b. Doing the same thing again, I have a point that I'm going to force it to go through. So I use that xy coordinate at 0, -2. So I get -2 is -1/3 times 0 plus b. Makes sense, right? That it should be at 0, -2 again, but if we always just do the math, it'll just fall out. -1/3 times 0, I'm gonna write it like b is equal to -2. So therefore, y is equal to -1/3 times x, -2. This one's harder to see in my head, I think. So I'm gonna plot it, just check it using Desmos. And so now I have -1/3, bump that out times x minus 2. Okay, looks good. Has to pass through 0, -2. And that looks perpendicular to the red line there. Okay. Nice. So I will get you to do something like that on the test, right? Find a line that's perpendicular to this line, right? Passing through some point or parallel, but more of a challenge if I do perpendicular, right? But you can do it. Okay. I'll highlight this because I don't want to write the blurb again. Even here, right? I can click these points. Now this first point, just because I don't have a pointer in Desmos, this first point, 0, -2, we force that. So that's kind of boring, right? We force that intersection. What about this intersection? How do you solve for this intersection? This is where this red line and this green line have the same XY point, right? And so the next thing that we're going to do is we have to find intersections of two lines. Yeah. And so here, I'm going to take a screenshot of this so we can see it. Done. So the graphs of two lines will intersect if they are not parallel. The only time that they don't intersect, right, is if they're parallel, then they never, ever touch. Even if the lines are just slightly kind of leaning towards each other, eventually they will cross and there will be some intersection. But if they have the exact same slope, then they never cross, and that's the only time. So they're going to intersect at a point that satisfies both equations, right? So some XY coordinate that satisfies both of those equations. And so we can solve for an input value where f of x is equal to g of x, where f of x is the first line and g of x is the second line, or vice versa. Okay. And so I'll bring in, oops. This little guy, hey. Come on, there we go. So what if we want to find, now we have the answer here, but that's always nice when you can kind of work towards an answer, right? Talk yourself into it. So find the point where f of x is equal to the red line, 3x plus 1, and g of x is equal to the green line, which is -1 over 3x minus 2, intersect. So what we're going to do, by setting f of x is equal to g of x, what are we really forcing? We're forcing the output to be the same. Right? We're forcing that y to be the same. And so set f of x equal to g of x and solve for x, and solve for, I'll say, the x that makes that happen. Now I'm gonna bump this to next page. Okay. So if we have f of x is 3x plus 1 and g of x is -1 over 3x minus 2, then we'll start here at f of x is equal to g of x. So then 3x plus 1 is -1 over 3x minus 2. To solve for x, we need to collect like terms, right? So we need to collect the x's on one side, and I like to have the just the numbers on the other side, just for simplicity's sake. So I also don't like negatives. So I'm gonna add 1 over 3x to the left-hand side, moving the x's to the left-hand side, and then I'm gonna subtract 1 from both sides. Okay. And so this is where it's kind of a choose your own adventure at this point, right? How are you going to collect like terms? Just do whatever whatever looks the most fun / probably the easiest to you. So I get 3x plus 1 over 3 times x is -2 minus 1. Right? Doing a little switcheroo here. We need to collect like terms. Sounds like they're having a social hour in there. First movies, then just chatting. I want to be in that class, I think. I can pull out a common x here. So I can get x times 3 plus 1 over 3 is -3. Careful when you're adding fractions, right? You have to have a common denominator. And so what I like to do is, right, 3 over 1 technically, but then I'm going to force a common denominator of 1 times 3 by multiplying this first term by 3 over 3. Yeah. And so here, how can I squeeze that in? I can't. I need to make a little bit of room. So times 3 over 3. That didn't look very good, did it? And times 1 over 1, technically. I don't tend to write those out, but just so we see it. So then I get x times 9 plus 1 divided by 3 times 1, which is 3. 3. So then it's just waking up. X times 10 over 3 is equal to -3. I'm going to divide 10 over 3 over to the other side. How am I going to do that? Again, technically, what you're doing is you have a fraction over a fraction. Right? And so here, x is -3 over 1, technically, divided by 10 divided by 3. Notice how I do a big line here to indicate that I have a fraction over a fraction. Right? If you want to skip, if you want to skip straight to -3 over 1 times 3 over 10, that's fine. But I want to show you where it came from. So we need to get fluent with working with our fractions. -3 times 3 is -9. 1 times 10 is 10. And maybe just for some space saving, I'll do that. -9 over 10, you could say that that's -0.9. You wanted to, right? I always check on my calculator. If I can get a nice number, then it's probably nicer to visualize with the decimal. This looks familiar, right? X is -0.9. Looks familiar from here, right? So now we have that value of x at the intersection. Right? Doesn't matter which line you put in x equal to negative 0.9 to find the y? No, right? Because we need them to be the same. So again, I just encourage you to pick the easiest one, right? Don't do anything hard unless you have to. Right? And so now we can find the y coordinate when x is negative 0.9. I didn't do any rounding, so I'll just say it's equal to. Doesn't really matter, but I'm going to use the first one just because it's a little bit cleaner, no fractions, no negatives. So then 3x plus 1, so f of x is 3x plus 1. F of negative 0.9 is 3 times negative 0.9 plus 1. First, let me confirm. Okay, good. Negative that times 3 plus 1 puts me at negative 1.7. That's a relief. We already knew the answer or what we were looking for, right? But usually that's not how it is, right? Usually we use it to confirm. So then the y coordinate is negative 1.7, which we can go back up and check. All right. Let's do it with the g of x just for kind of flexing our muscles a little bit. How about I move this over just a smidge? Or g of x, which is negative 1 over 3, oops, 3x minus, what was it, minus 2. G of negative 0.9 is negative 1 over 3 times negative 0.9, then minus 2. Negative 1 divided by 3 times negative 0.9 minus 2. Surprise, surprise. They have to be the same. We're forcing them to be the same. But that's a good way to check it, right? So therefore, the lines intersect at, bless you, negative 0.9, negative 1.7. It turns out, let's make up some different lines here. These are the same. Do I go rogue? What do I have here? Let's find where f of x can be 2x minus 3, and g of x, let's do, is 1/2 x plus 1. Okay. So if we have to find this intersection, now I'm holding off on graphing these because obviously that would give us some clues, but we know what this looks like, right? I've got a positive slope and a negative y-intercept. So f of x looks maybe something like this. Okay. I've got a positive slope again, but kind of slow, right? Here's a quick slope, here's a slow slope, just because it's small, +1. So then I've got kind of a, maybe something like this. So it will be useful to be able to kind of visualize what these lines look like, right? I'll never get you to draw lines. I think that's really quite dumb, but being able to see them in your mind or even sketching them out. Notice I'm not drawing any ticks or anything. I'm just kind of sketching out roughly where they would go, right? And so this tells me what about my answer? I'm expecting my intersection to be at a positive value of X and a positive value of Y, right? And so that's telling, that's something. Okay, what do? We set them equal to each other. We solve for X, or the X that makes that happen, and then we can plug in that value of X and solve for Y. And then we'll have the point. Okay. Can try it. How about this? We'll do I'll write it out, but I want you to try it on your own, and then we'll kind of check back in. I did both f of x and g of x to solve for y, just to make sure I got the same thing. Let's get back here. Set them equal to each other. Collect like terms, right? Bring the x's to one side, non-x's to the other side. And then for practice, right, just working with those fractions, right? Get a common denominator if I'm adding or subtracting fractions. I get 2 over 2 to force this common denominator of 2 times 1 technically, but I don't really care about the 1. 4 minus 1 over 2 is equal to 4. I end up with, when I divide 3 over 2 over to the right-hand side, right? I get technically a fraction over a fraction. Now, I didn't write the 4 over 1 like I have been doing. All right, we're going to kind of grow out of that, but it's there, right? It is a fraction. So then 4, and then for the denominator, you have to flip and multiply, right? So 4 times 2 is 8 divided by 3. So x is 8 over 3. Now for practice, I kept the 8 over 3 because if you do it on your calculator, 8 divided by 3 is 2.66 repeating. So I don't want to be rounding that, right? I want exact answers. And so now 8 over 3 is the x that I'm going to put into. Now you only have to show one of these, right? I'd say the putting it into f of x is a little bit easier than g of x, but took the same amount of steps, so it doesn't really matter. So wherever I see an x, I'm going to put in 8 over 3 and solve for the y. So 2 times 8 is 16 divided by 3 minus 3. I'm going to force a common denominator of 3, so times 3 over 3. Right, that trick of just multiplying by 1. Putting me at 16 minus 9 over the common denominator of 3, so 7 over 3. Now, these numbers aren't very nice, right? But let's see what Desmos has to say about it. Oh no. Let's see here. There's something about which side I put it on. I had it like this, but the other way around, and it wasn't showing. Anyways, weird. 2x, hopefully that hasn't happened before, minus 3. Looks how we expected it to. That's a relief. And 1/2 times x plus 1 also looks how we expected it to. And we get the intersection, which is the same as what we had. Oops. And I crop this. Hey. I don't know why, but my iPad is being so sticky. We did it. Found where 2 lines intersect. Okay. Is that all that's it. Any questions about intersections, parallel, perpendicular, just properties of lines in general? Okay, so what I decided is it doesn't really make sense for us to do 2.3 together, because I think it's a really good opportunity for you to try these questions on your own. And I'll post the solutions and we'll see if I can remember to make a video of the solutions so that you can have a video to watch. But hopefully just the solutions are sufficient, right? But here in section 2.3, we're just kind of problem solving, right? And so if you read the section, it just talks about, how do we problem solve, right? That's not something that I can kind of spoon feed you. I can show you how to solve exactly this problem, right? But the steps for problem solving, you kind of have to get there on your own. And so I kind of changed my mind last night. We're gonna just try this on your own, 2.3 on your own, and then we'll pick up 2.4 instead. But like I said, I'll post the solutions, and some of these are perfectly reasonable. Some of them make you think about things a little bit. Duplicate. Okay, just rename this here. There's an Excel sheet posted on Moodle with this data in it. And so let's see if I can, I think I just have it here. Hey, this is old. Maybe I do need to grab it. I posted it with the lecture notes. Let's see if I can download it on here maybe. Okay, so the first tab has the data, which we're about to talk about. And then in the second tab, I did it because it's really hard for me to do on the iPad because I don't know, the functions are different. They're not different, they're just reduced. So I figured I'd Martha Stewart it, pre-bake it, give it to you. So linear models are extremely useful and used in statistics. And so in statistics, we fit linear models, which just means, okay, if I have data like this, right, then I can fit a model to model this behavior, right? We have data points that tell us, individual situations, but
Yeah, so
huh?
The D2 temperature should be.
Oh. Yeah, so, okay, so we've got the number of cricket chirps in 15 seconds and the air temperature. And I'm guessing that this is by day or something like that, but you could rearrange them as long as you keep the XY coordinates linked up, right? You could sort them. But we're kind of cheating because I give you the graph right away. But it does say plot the data. What's one of the things that you have to decide before you can plot the data? You have to plot or decide which thing is going to go on your x-axis and which thing is going to go on your y-axis. Sometimes it doesn't matter, okay? But what we want to ask ourselves is, okay, if I say on the y-axis, we're going to have what's called the dependent variable, meaning it depends on whatever is on the x-axis. So on the x-axis, we're going to have the independent variable. So then, right, to try to figure it out, you ask yourself, does one variable depend on the other? In this case, if we're talking about the number of chirps in 15 seconds and the air temperature, right? I'm gonna go ahead and say that the chirps depend on the air temperature, right? The air temperature doesn't really depend on the number of chirps. The weather goes, oh, right, let me just adjust. No, right, it's the other way around. And so in this case, right, on our y-axis, y is going to be the temperature. Yeah. No. I just talked myself into okay, I don't like that. Should have the other way around. You know what? We're just going to fix it. On the y-axis, right, the one that depends on the other variable, right, the chirps depends on the temperature. And on the x-axis, the temperature doesn't care about the chirps, which means that I don't like this. I didn't catch that. Oh, can I fix this on my iPad? Time will tell. Ooh. Just so I don't have to undo everything, we're gonna use what we're given, where the temperature is on the y-axis and the chirps is on the x-axis, but we will use what is given. Otherwise, the rest of the questions are going to be they're going to require work to fix as well. Note to self, fix this, fix it. Okay. That's okay. Maybe I shouldn't have these X's on here then. We do a lot more stats in Data Science 228, which I think you don't get to take until next year, term 2 next year, but then we'll do stats. And then I'll care about this. But this is just showing you how to fit a straight line, so not too bad. All right, so I remember in maybe chemistry 11 or 12 or something like that, where we had some scatter plot like this, right? So you've put your XY coordinates on a graph, and then you have to fit the line of best fit. And what did we do? You just kind of eyeball it. You say, oh, that's pretty good. Not quite how we actually do it, but the idea is the same, right? And so we fit a line of best fit which is a linear model. There. To model the relationship. That's what I could say. To model the relationship. Yeah. Ultimately, what we want to do, and I think I give up, I need more space. There. We model a relationship usually in order to, well, be able to talk about the relationship, but also to predict values of y. Right? And so we model relationships to be able to predict values of y. And I think I'm gonna need a lot more there. Oh boy. Okay. This thing. Okay, good. So in that spreadsheet that I posted, right? You guys been working a lot with Excel yet? Or not?
Not really.
Not really. It's kind of, sort of.
Here and there.
So here I've got data tab. I've got a data tab, and then I've added the scatter plot because if we do insert, yeah, you can see what I'm clicking, although it's kind of weird. Insert, and then I can go to chart. Obviously, this is the iPad version, so it's not great. But then I just pick the first one. And whatever I have in the first column is going to be the X, and then the second column is going to be on the Y-axis. So if you had to reverse these, right, so that would be something I would have to fix if I wanted to change it. So you've got your X and your Y, and then if you want to switch these, because you might be tempted by the switch row column, but it makes it wonky, so it doesn't do that. So then you have to copy this and move it over here in order to switch it, which I honestly don't know if I can do properly on my iPad. It's more of a medium screen problem. So I made some adjustments to this basic plot on the next line or on the next page. Okay. I've done things like I put a title, a proper title. I put the y-axis and the x-axis, what they are, so it's easier to read. And then what did I do? I asked it to add a trend line, which I could not figure out how to do on the iPad. But what you do is you click on a dot. Well, okay, it won't let me do it, but that was the whole problem. it only lets me select the whole graph. But if you click on a dot, then you can, so if you're in here, let me see if I can, no, still no. You right click on a dot, add trend line, and then at the very bottom, you can ask it to add the equation. I also add the R squared, which I'll talk about. It's not in the textbook, but so here it gives us this regression line. The regression line is just the line of best fit, and there's a lot of math that goes into it, right? But we don't really need that right now. We just need to know that, okay, this is a straight line, and what's the number one thing? If you're using a line to model the relationship, first thing you should probably check is to make sure that, does it follow a linear pattern, right? A lot of your guys' measurements are going to be maybe exponential, right, in nature. But for us, we're just talking about linear models today, okay? And so, because that's what we're working on. Now, can I, since it lets me select this, can I copy this here and bring it in here? No, it does not. Great. Screenshot it is. Just trying to. Line it up. Okay. I'll crop top this. Can't crop it too much though. So here, I encourage you to play around with making the scatter plot, maybe even moving the X and the Y's around and see what happens. And then obviously you won't have Excel on the test, so it is just for fun, right? Just to play around with. But it's nice to have seen something like this. And so then, and also make sure that you're able to add a trend line with the equation on the graph, just like this, right? Okay. And for good measure, we can throw in the R squared, right? So here, we're told that Y is equal to 1.1432x plus 30.281. I don't know about you, but I cannot get there with just eyeballing it. Probably wouldn't have that line, right? What this line is doing is it's reducing the distance from all the points. In fact, it's reducing the squared deviations, but now I'm getting carried away. It's called the least squares regression line, but all we need to know is that, okay, this is the line of best fit. We're also told that R squared is 0.9043. The R squared value you'll see in other courses before we get to the stats course next year, and so it's nice to introduce it here. It tells us how well this line fits the data, so how much activity is captured. It assumes that you have a linear equation, otherwise, or a linear relationship, otherwise it doesn't work, okay? But an R squared close to 1 is really good. Okay. High R squared values, right? Which means that it's close to 1. R squared you can convert to a percentage, and so 90.43 is pretty good, close to 100. And so close to 1 tell us the model is doing a good job. At predicting y. So that's good to know. That's good to have up our sleeves. What's a low value of r squared? Probably like 0.6. So anything kind of close to 1, 0.9 is really good. I'd be thrilled if I found a 0.9, right? I've made it work with a 0.5. There's hardly any relationship there. What does that look like? It means that there's just scatter everywhere. Okay. And now, well, first let me see. Oh boy. Okay. Let me just give myself some space so that I can add a page. I didn't do a very good job of anticipating how much I could blab about this stuff. Did I? There. I'll pull them up as I go. Okay. Okay. So a high r squared is what you want, as close to 1 as possible. Okay. And let's go back to this line of best fit. If y is equal to 1.1432x plus 30.281, what does the slope tell us? Remember that the general interpretation of the slope is for each unit increase in x, right, which in this case is for each additional chirp per 15 seconds, right, we expect the temperature to increase by 1.1432. Right? Let's add that in. For each additional chirp per 15 seconds, whoops, we expect the temperature to increase by 1.1432 units Fahrenheit, but just go units. What about the intercept in this case? Now that we have kind of things that x and y represent, the intercept is 30.281. The intercept is when x is 0, that's your value of y, or what you would expect your value of y to be. So if there are 0 chirps per 15 seconds, if there are 0 chirps, right, if x is 0 per 15 seconds, we expect the temperature to be 30.281. I'll say degrees Fahrenheit. Just as a fun fact, I guess they stopped chirping at 50 degrees Fahrenheit. It's just, and then as it warms up, they chirp more and more and more and more. Cute. But that's what we would expect it to be, right? Lines keep going forever. And so that's just where it would cross the x-axis, or sorry, the y-axis. However, so that's way over here, right? If this line continued, then it looks like it would be somewhere around here. Fair enough. However, we built this line using values of x within kind of, I guess we have the data, but let's say 17-ish up to 45-ish, right? So we built this line using values of x between roughly 17 and 45, right? Even we could take it to 15 if we wanted to, but and so this line is really only valid for that range, right? So here, what is this this value? 17-ish probably. I think 18.5, is that the smallest one? Okay. So here, notice we built the line using values of x between 18.5 and what was the maximum here? And 44, I think. And 44. This means that it's really only valid for predictions in this range. We can go out a little bit, tiny bit, right? But not too far. And so this means our line of best fit, or more properly, our regression line. If you hear regression, it's really just the line of best fit, so nothing crazy. And so, so this means that our regression line is only valid within this range, valid for predictions. Now I'll grab this. So interpolation, inter means between, right? And so if you're making predictions kind of within the range of the data that you built your line from, it's called an interpolation. So when we predict a value inside the domain and range of the data, I'm just talking about the domain, the values of x, because the range follows, right? Extrapolation is when you're predicting for values outside the domain of the data, right? And so when we make predictions such as 0 chirps, right, for 15 seconds, then I predict that the temperature would be 30 degrees Fahrenheit, 30.281, right? That's an extrapolation, because 0 is way outside of the domain of our data. Usually I call it the range of the data, which is weird because it's not on the y-axis, but the domain of the data. We saw the y-intercept is an extrapolation. Ugh. would predicting the temperature when crickets are chirping 30 times in 15 seconds be an interpolation or an extrapolation? And so we're going to make the prediction and then we're going to talk about if it's reasonable or not. But I want to snag this so we can see it. Copy. "30 chirps per second is here. So our prediction, our predicted temperature is whatever we can map back to on the y-axis, right, from this line. That's our best guess, using the data that we have. And so we have from the output, y is 1.1432x plus 30.281. If you prefer, you can rewrite this as the y is the temperature and x is the chirps, just to kind of remind yourself that, okay, I'm getting a temperature and I put in the chirps. So here, or if you prefer, the temperature is 1.1432 times the chirps plus 30.281. Either way, I'm going to let chirps be 30. 1.1432 times 30 plus 30.281. 1.1432 times 30 plus 30.281. Uh-oh, sorry. It's important that you multiply these two together first, right, before you add the other one. So I'm going to not jump ahead to that, and I'll write out this middle step here. 34.296 plus 30.281. Now I can add it. 64.577. Does that look reasonable?
Yep.
I think so. My line's a little off, but good enough. Okay. This is an interpolation. I guess I skipped that part, so we just talked about it, right? But 30 is between 18.5 and 44, and so it's an interpolation. I'll just highlight that here. Because it's an interpolation, it is a reasonable prediction. Okay? And so since 30 chirps is an interpolation, it is a reasonable prediction. Or maybe I shouldn't say it. 64.577 degrees Fahrenheit is a reasonable prediction. Oh. Good. This one, we need to be a little bit careful. Maybe I'll put it on the next page. Yes. Take this guy again, copy. this one we have to read carefully. Would predicting the number of chirps crickets will make at 40 degrees be an interpolation or an extrapolation? Now, let's remember that, okay, chirps is on the x-axis, which means that 40 degrees is here. Right, this is at 40 degrees Fahrenheit, but whatever. I don't have any y values there, right? It doesn't hit the line or anything. Technically, if we extend this line, right, we said, okay, it's going to go like this. So we can find this point. But it's an extrapolation, right? So this point, we can work backwards like this, right? But it is an extrapolation, making it not a very good prediction, right? Or not a very reliable prediction. They really do. Especially in the news and stuff. They're constantly extrapolating. It's crazy. So now I think once you kind of know to be aware of it, it happens all the time where they're just, oh yeah, in 2050, this is going to happen. It's like, well, things change, right? But yeah, so it is our best guess, and that's where we kind of run into problems is, okay, it is our best guess, but we have to kind of be upfront about it's not very reliable because it's an extrapolation, right? But we can still do it. So how about we write it like this? The temperature is 1.1432x plus, or sorry, times the chirps. Plus 30.281. Is this clock right or wrong? Can't see. No, it's right. Okay, good. Okay. So we're going to force the temperature to be 40 and solve for x, or solve for the chirps. So 40 is 1.1432 times, can I just call it C for simplicity? We can use T and C instead of writing it out. Plus 30.281. See ya. Throwing me off. You know what? That's fair. I don't mind, but I rely on those cues to tell me when time's up. So yeah, that's I have more to say. Not a lot more, but some more to say. Okay, solving for C here, we can rearrange first, right? Trying to get C on its own first. I'm going to subtract the 30 over to the left-hand side, right? I need to kind of pick away at this onion. And so I get 40 minus 30.281 is 1.1432 C. 40 minus 30.281 puts me at 9.719. But what am I going to do? I'm going to pull a fast one here. C is 9.719, which is just this side. And then I'm going to divide by 1.1432, but on the other side, because I've swung it around. Swing your partner round and round. So divided by 1.1432, I get chirps 8.5015745528, or roughly 8.5 chirps, which if we kind of map down here, that looks reasonable, right? That looks like the answer, but because, so here at 40 degrees Fahrenheit, we would predict approximately 8.5 chirps per 15 seconds. However, since this is an extrapolation, right? However, since this is an extrapolation, it is not a reliable prediction. Good. But on the test, if I give you a scatter plot like this with output, giving you the least squares regression line, right, then I do want you to be able to make predictions, but also identify if you're interpolating or extrapolating, right? Extra meaning outside. Okay. I think. Correlation is related to that R squared that I put up, but correlation is, I'll write it here. The correlation, or maybe I'll say the correlation between X and Y, is a numerical measure of the direction and the strength of a linear relationship. Is a numerical measure of the direction. All right, so positive or negative and strength of a linear relationship. Has to be linear. Right, so it has to follow a straight line. Otherwise, it'll still calculate it, but it doesn't mean anything. It doesn't tell us anything anymore. Yeah. And so usually correlation, let's do a little line here. Actually, it ends. Correlation runs between -1 and 1. Put 0 in the middle. Okay. Now, correlation is usually denoted by a lowercase r. And I'll bump this down. Okay. So just as a quick guide, anything between kind of negative 0.5 and positive 0.5 is going to be considered weak, a weak relationship. Now, of course, here we have negative values, so that tells me that it's a negative relationship. A negative relationship means that the slope of this line is negative. Versus between 0 and 1, and now I have a positive correlation, which means it's a positive relationship, which means that my line has a positive slope. So knowing the correlation tells me something about the slope as well, or at least the value of the slope. In fact, the correlation goes into the calculation for finding the slope, but that's not for this course. And then here, kind of outside between 0.5, now I'm using round brackets because it's kind of, you know, a little bit movable, but you can have a strong positive relationship, meaning that the points are really close to the line, or a weak relationship means that the points are moving further away from the line. It's kind of, you know, your line's not doing a great job. Or you can have a strong negative relationship. Strong meaning it looks like this. Your points are kind of close to the line. And a negative relationship still close to the line. A weak relationship just kind of looks like this. Just cluster. It doesn't really matter where you put this line through this cloud, right? And so that's what makes it a weak relationship. So in this case, right, it would look like this. Those aren't very nice dots, are they? But just... But as you move further out in either direction, right, the lines become, or the points become closer to the line as you move out and increase your correlation. Okay. So let's talk about, so a correlation is usually denoted by a lowercase r, and it's between -1 and 1. Okay. A positive r means that we have an increasing relationship, and a negative r means we have a decreasing relationship, but we just saw that. The closer the value is to 0, the more scattered the data is, right? And the closer the value is to 1 or -1, then the tighter around the line it is. So just a summary of what we said. Okay. A little fun fact. R squared is the correlation squared. Okay. So R squared is the correlation squared. I guess when we square it, it graduates to a capital letter. Okay. But what does that mean? It means that if we have the R squared, so then therefore, the correlation is the square root of the R squared, but it's plus or minus depending on if you have a positive or a negative relationship, right? So from our graph, we were given the correlation, or sorry, the R squared is 0.9043. We have a positive relationship, right? So the correlation has to be positive. Okay. So 0.9043, let's see if I can remember that. So we are given R squared is 0.9043, and we see a positive relationship. So the correlation is the positive square root of r squared, which is the square root of 0.9043. Square root 0.9043. I get 0.950946. I'll call it at 9. I have a few more, but. So this tells me that I have a strong, right? A correlation of 0.95 is very strong. It's very close to 1. And I have a strong positive linear relationship. We can confirm this with the Excel output because I also included it. Why is this slightly different? Because we used rounded values, right? These are rounded slope and intercept, but I think that's pretty good still. Oops. Copy. Or from Excel. Differences are due to us using rounded values. If we use the proper values, it would be the same, right? But I think they're close enough. Right? So now, even if I just give you a graph with the model, right, the least squares regression line and the r squared, you also know how to find the correlation, right? Just remember, if it's negative, you have to tack on that negative, right? Because you lose it when you square it, right? So then if you are unsquaring, you need to bring it back. Any questions about that one? Before we do our, well, I'll check before I say it's our last example, but I'm pretty sure. So sometimes, I think on the assignments you get output like this. So a regression was run to determine if there's a relationship between the diameter of a tree, which is the x in inches, and the tree's age, which is the y in years. So we're told the x and the y in this case. The results of the regression are given below. Use this to predict the age of a tree with diameter 10 inches. And so the diameter is the x. And so here, this is saying let x be 10 inches. Careful about units there, but I'm not trying to trip you up. So usually they're the same, but just heads up. Output can look like this. It tells you the format, right, of y equals ax plus b. So that means that a is the slope because it's attached to the x, and b is the intercept because it's on its own. And then it tells you that a is 6.301 and b is negative 1.044. So from this, I can build out that y is 6.301 times x minus 1.044. That might be helpful. Just putting all those pieces together instead of it being given to you just explicitly. We're also told the r squared. Now they've used the lowercase r squared. That's fine, it can happen. And the correlation is positive, which I can check. Does that make sense? Yes, because I have a positive slope. So all good, right? And so you can confirm if you take the square root of 0.94, you should get 0.97. Square roots of decimals are weird, right? They don't behave the way I think that they should. But the square root of 0.94 is, well, they've done some rounding, but 0.97. Okay, but we wanted to predict the age, which is the y, of a tree with diameter 10. And so y is 6.301x minus 1.044. So y is 6.301 times 10 minus 1.044. Multiplying first, 6.301 times 10 is 63.01 minus 1.044. I predict the age to be 61.966 years. Notice the slope is positive. I'll just write out what I said earlier. So R is also positive. And R is the square root of R squared. Positive square root of R squared. Square root of 0.940. Just noticing that relationship. Okay. Any questions about those? Yeah.
What does the correlation have to do with the diameter? With the age?
So,
Like I can see you plug it in anywhere. Just,
oh, this is just a separate note.
oh, okay.
Yeah, sorry,
What
there.
would it have to do with
So the correlation is telling you just the strength and the direction of the relationship. It's unitless, which is kind of a nice property of it to have. So it doesn't care which one is the X and which one is the Y. It's just telling us that the age and diameter of a tree are moving closely together in a positive way, right? They're increasing together, which makes sense, right?
Higher the correlation, the more accurate prediction could be.
Yes, we use the R squared for that, but they're very closely linked, right? So usually we rely on the R squared being close to 1 or 100%, and then that gives us a strong prediction. Nice. As long as we're interpolating. Tightrope. All right. Any other questions? No. Okay. I've posted these assignments, but I think I made them do the 14th, thinking our test was on the 15th. But what I can do is I can bump them to the 16th, although it might be nice to get them done, but I just want them to be due before the test, right? You should be working on them as practice. So I'll make those changes. But okay, good. Have a great weekend. See you Tuesday.